part of the NEWAVE Diffused conference. My name is Paulina Raniecka, and I am an affiliated researcher at NEWAVE. It will be my pleasure to moderate today's seminar. I am stepping in for NEWAVE Scientific Project Manager Caterina Marinetti, who couldn't be with us today. Today is the 14th session of the thematic seminar series, which started at the beginning of April and will be accompanying us until the end of this year with bi-weekly online webinars. The thematic seminar featured the NEWAVE early stage researchers who guide us through the key water governance aspects that they have been investigating during the NEWAVE project. Today's seminar will start with Wenjin Hao's lecture titled Harnessing Machine Learning for Urban Water Demand, Unveiling Predictive Powers and Key Determinants. Dr. Wenjin Hao is a postdoctoral researcher at Politecnico di Milano, Italy, with a strong interdisciplinary background in AI, climate science, and environmental engineering. She holds a Master of Science degree in environmental engineering from ETH Zurich, where she specialized in urban water management, and a PhD in information technology from Politecnico di Milano, where her research focused on urban water demand modeling through machine learning for forecasting and key determinant identification. Currently, her research centers on AI-enhanced climate services for drought monitoring in Africa. Together with Wenjin, we welcome her PhD supervisors, Andrea Castelletti, Professor of Natural Resources Management and Environmental Systems Analysis at Politecnico di Milano, and academic guest at the Department of Civil and Environmental Engineering, ETH Zurich, and Andrea Cominola, Assistant Professor of Smart Water Networks at the Einstein Center Digital Future and TU Berlin. I kindly remind you that you can submit your questions during the seminar at any point using the Q&A function. The moderated Q&A component will take place towards the end of today's session. Thank you so much and enjoy the seminar. With this, I will pass on to Wenjin. Good luck and enjoy. I'll wait for you to share your slides.
Yeah, thanks for your introduction, Paulina. And I'm going to share my screen. Okay, I guess you can see my screen.
Yes, it's perfect.
Presenting mode. Okay. So I will start of the sharing of my PhD research. And first, I want to apologize because I'm sick, so I hope I'm not coughing a lot during my talk. So today I'm going to present some key findings of my PhD research about machine learning applications for urban water demand modeling. So a brief introduction for some background knowledge. The urban water is a key resource in cities, is now facing challenges from two aspects. One is climate change, one is urbanization. Climate change has resulted in more frequent extreme events, which lead to the uneven distribution of water resource, which limits the accessibility of water to the urban context. And with increased urbanization, more water is consumed in cities, which stress the imbalance between water supply and demand in urban context. This has already led to 25 countries facing water stress annually, and which will be more severe by 2050. So it's important to comprehensively manage water in cities. On one hand, we can looking for more and explore more water resource and build more supply infrastructures. But on the other hand, we also need to better understand how water is consumed by people in cities and industry activities, and also anticipate the future water need to better supply enough water. So by understanding these challenges in the urban context, the machine learning techniques have shown potentials and have already been used in the whole urban water system management, from anomaly detection to system prediction and system operation by using some advanced structure like convolutional neural network, long short-term memory structure, and also reinforcement learning to detect leakage of the water, contamination in the water, and also forecasting of system states or water level and water quality forecasting, and also operations of pumps. But this machine learning methods still facing some common challenge, like there are probably lack of large data size to develop a model, and also we need spend quite some time to clean and process the data, and also we lack some general structures or shared structures of trained model from one case to another case. And the other key point people are asking here that in many cases, the machine learning model has been performed as black box model, that data goes through the model and then got the results, but people don't really know how the model make this decision. So researchers are also focusing on improve the interpretability of the model to better negotiate, to better communicate with decision makers about how the model process and make decisions when you got such result by using some specific techniques, for example, post hoc process of result or inherent model interpretability. So in my PhD research, I explored two research pathways in urban water demand modeling. The first one is how can deep learning and hybrid modeling framework can enhance the accuracy of forecasting at multi steps, and also evaluate the robust needs when facing some unseen demand patterns at city level. And the second pathway is to understand what are the driving factors of urban water demand at large scale. So for the first direction, we develop a comparative analysis for multi-step demand forecasting. We compare different model structures from simple statistical to machine learning models and focus on short and medium term demand for 1 day and 7 days. Some model structures I want to introduce here. The first one is the time series model, for example, the autoregressive integrated moving average, which has been already used a lot for time series forecasting task because it is simple and directly model the data structure. So it's easy to implement and understand the process. However, this model assumes linearity in data, which is not real in the complex system, for example, the demand use process. So that's why a lot of research starts to use neuron-based model. The most popular machine learning model type to make the demand forecasting. For example, there are two types of structures, the feed-forward neural network and the recurrent neural network. For the first one, the information flows from input layer to hidden layer to output layer to get results. But for the second type, we have the recurrent connection back to the model to capture the historical values and influence on the output results to better capture the influence of historical value on the predictions. And another advancement of such recurrent neural network is long short-term memory networks. It has special memory blocks to better capture the long-term dependency of historical data on the predictions. And then we further apply the attention mechanism, which focus on the most useful time steps that contributes a lot to the prediction to further improve the performance of the model. And then we also consider about the tree-based model and use a gradient boosting framework to train the model. Basically, this framework trains the model step by step to iteratively reduce the error. So by each step, one new tree model are added, and this tree model is specific to reduce the residuals from residuals of the performance from last iteration to targetedly reduce the error, and then eventually combine all the models together to a strong predictor. And then we choose the leaf-wise tree growth, which split the nodes of the tree at the nodes where will resulting in the largest reduction of the residual in the model. And this is like GBM model. And this model is used for prediction and also future selection. And so except considering different structures of the model, because we want to examine the model structure influence on the demand forecasting performance. We also consider about feature enhancement by wavelet transform. This is a wavelet filter moving along the time series data and then decompose the time series into scaling coefficients and wavelet coefficients. This is an example of post results. The scaling coefficients capture the main patterns of the original data, and the different wavelet coefficient capture the short-term variations at different levels to capture the short-term fluctuation in the data and remove the very small disturbance that is not useful for forecasting the original data. So after introducing the model structure and the ways we enhance the feature of the data, we introduce our case study. We collect the data from Milan, Italy. We got data from 2017 to 2020 daily data. So this is the plot for the temporal dynamics of demand patterns in Milan. That is, there is a overview seasonal fluctuation, and also changes are shown, like for example in August, people are going out for holiday, and the water consumption drops down a lot. And also because we covered the 2020, there is a period of COVID lockdown from 2020 March to 2020 May. So in this case, we can evaluate our models robustness by these unseen patterns before. So we develop our forecasting framework for the different model structures, and all the model structures are developed for using the data, original data, and the data decomposed by the wavelet, or the 1 day and 7 day forecasting. And the whole procedure, starting from the feature engineering to process the water data and the meteorological data, and then perform wavelet decomposition, and then perform the feature selection to select the most important predictors, and then develop models for different structure, and then follow a classical conventional machine learning training and calibration process. And the result part, starting from comparative analysis of 1 day ahead forecasting. So this is the evaluation matrix result for the different models using and not using the wavelet decomposed data. The blue bar shows the model using the original data, and the orange bar shows the model using the decomposed data. The first three metrics if the first three metrics have lower value, means the model perform better. The last two indicators, if they are more close to 1, the model performs more better. So from this plot, the first message is almost all the models, regardless with or without the wavelet transform, and across all the model structure, this model all perform pretty good, with the NSE value around 0.8 to 0.9, and but still performing the wavelet transformation can improve the machine learning model of by different degrees. And also, if you plot the time series of observations and forecasting the data, we can see that the lines are aligned with each other perfectly. So the conclusion from this result is that even machine learning probably perform slightly better than the time series model, but in reality, if you want to have a model that implements easily and quickly, and also simple to understand the structure, maybe the time series model is more pragmatic and straightforward compared to the machine learning and deep learning model. But if we move to the result, to the medium-term forecasting results, the deep hybrid model actually shows much higher performance when considering the time series model actually deteriorates a lot. For example, the NSE from 0.8 to 0.5, but the decomposed machine learning model, especially the neuron-based model, including the AN-LSTM and attention-based LSTM, perform pretty good, can have the NSE value almost approach to 1. And if we look at the weekly performance in the test data from 2019 June to the end of 2019, all the machine learning based model with the decomposed data perform pretty good across the weeks. And especially during the August holiday when the water drops a lot, the neuron-based models can perform pretty good while the time series model and also the model used in the original data cannot well capture that trend. And the last part of forecasting result is to test the model robustness during 2020. As I said, there is a lockdown period in April to in March to May, and we can see the model, the light GBM model with decomposed data, and SVR model with decomposed data cannot capture the decreasing trend of demand patterns during this lockdown period, but the neuron-based model with wavelet transformation can still well capture these patterns, even these patterns is not happened in the previous training process. So this demonstrates the deep hybrid model can well performs, especially the neuron-based deep hybrid model can perform very well when there are some structural changes happens. And the last part result is to check which features contributes to this forecasting performance. So we plot the light GBM feature importance. The higher value indicates this feature is more important for the forecasting. And this result shows the historical demand data and also meteorological variables are both K for the prediction of the demand, but there are some difference, like for 1 day ahead forecasting, the historical water demand and the weekday indicators shows more higher feature importance, but for the medium term forecasting, the historical meteorological factor also shows importance. So the take-home message here for the first research direction is that since there are limited comparative analysis of different model structures on multi-step forecasting study, and also there are limited cases evaluate how this model structure are sensitive to the abstract data change due to the external stressor, we propose this hybrid framework combining wavelet transform like GBM and deep learning models. And the key findings shows this model structure and framework can really improve the accuracy and robustness during the forecasting and also for data with structural changes caused by external stressors. And then let's change to the second topic about understanding the driving factors of demand patterns across continental scales. So for this research line, we consider the demand patterns over the continental US. So we collect data from public source for 86 cities in US for monthly data, and then we plot this daily total demand per capita and daily residential demand per capita plots over the US to intuitively see the distribution of the water use. So it's clear that in US actually the smaller cities have more water use, and the cities located in arid region have relatively higher water use. And then we further plot the anomalies of some meteorological indicators and the total water use to have a perception about the relationships between the climate and the water use. So we can see for the dry period that we have high anomalies of vapor pressure deficit and temperature, while at the same time we also have higher water use at that period, which indicate a bit the relationship between climate and the water use. So to understand the drivers the drivers leading to the demand patterns in US, we collect different variables to consider. In total, we considered 32 variables, considering the demand patterns process is a coupled human nature system. We collect variables from social demographic to housing characteristics and economics and climate. And all these data are collected from public source as well. And then to map the relationships between the drivers and the water demand, we use the Granger causality, which is simply statistical test to check if adding one times historical value of one time series can help improve the forecasting of the future of another time series. So this Granger causality have a simple assumption about predictability implies causality, but the original Granger causality focusing on the linear relationship of the predictor and the target variable. So we adopt a neuron-based Granger causal model using the neuron networks to explore the nonlinear Granger causality again. So the experiment setup are shown here. We start from the data preparation to compare all the data source about the demand and the determinants, and then cluster the data into different climate regions, and then develop the neuron Granger causal model for the whole US and for 3 climate regions here are arid, temperate, and continental regions. And then we do have a primary training, which is important for improve the model performance, and then k-fold cross-validation and the result analysis. So the first part of the result is still forecasting for performance, because in this case, we are also care about the forecasting performance as well as the driver identification. So the first plot is how model performs across the whole US and across the climate regions. So different colors represent different scenarios. From scenario 1 to 5, the numbers of determinants are different. So 1 to 5, from 1 to 5, the determinants are numbers of determinants are increased. From this plot, it's clear across all the selected scenarios and for all the models, the mean R square here is the similar measures of accuracy. That's value approach to 1 is represent higher performance. So mean R square here is 0.85, which is pretty good. And for arid region, actually the R square can over 0.9. And the best scenario we select by this red square is plotted on the maps again for the whole US and for the combined climate region models. So for the whole US in the upper figure, we saw the different cities have quite similar good forecasting performance, but for the combined climate region results, there are some cases, there are some cities are not very well forecasted. For example, the city Blacksburg City. For the continental models, it cannot really well capture the patterns, shows low predictability. But in general, the most cities can achieve high performance already. And then we check the selected Granger causal determinants for the demand in continental US and in different climate regions. Here, the different color shows different categories of the determinants, from climate to social demographic to economic, and the best scenario are still shown here by the red star. So the first information here is that for the first figure for the whole US, only historical water use here we call memory effect, and the vapor pressure deficit, which is an indicator of the dry condition, can contribute to the best performance. But for the climate regions, the more determinants like the other climate variables, for example, temperature, contributes to higher accuracy. And social demographic characteristics might have predominantly local effect that it doesn't shows up really in the whole US model performance, but it contributes for example, the arid region and temporal regions performance. And this is also reflected by the feature importance results. We plot the predictor feature importance by this Neuron-Granger corral model for the whole US and the climate region. And we can see the identified climate variables actually have high feature importance, which is comparative to the historical water use. But if you look at this identified social demographic ones, it has relatively low feature importance, indicating they have a relatively low contribution to the prediction. I think this is because of the low change of the social demographics and also the annual frequency data collection of this data. But even these social demographic factors does not contribute a lot for the forecasting, but it's still useful for qualitatively understand how they might influence the demand patterns. Here is an example that we cluster the demand patterns in arid region using the identified population density and the building construction year. We cluster the residential water use and total water use demand pattern, the patterns into different cluster, and we identify 2 clusters have statistically obvious decreasing trend. Both cluster have either have small population density or large population density, but they both have relatively more old buildings built after 1990. So this reduced water use during this period might be due to the inefficient use of the older infrastructure and the influence of the dry condition before 2050. So this analysis can help us to understanding better why the demand patterns are changing in some cases, but not changing in other cases. So the take-home message here is that there is a need to deepen our understanding of demand patterns of large spatial scales to have to facilitate more large-scale demand strategy planning. So we propose this framework using the Neuron-Granger corral model to examine the different categories of the variables that might have influence on the demand pattern. And our key findings find this model can achieve high accuracies with only the historical water data and the climate variables. So the demographic ones shows less predictability, but it has some local insights to understand the demand patterns over different cities. So, and now these are 2 main finished research line in my PhD, and then we are still ongoing with the last direction that we want to integrate the forecasting with control strategy for the urban water network, because in the control works of the water distribution network always simplify the demand that either have using the average values or simply considering 1 day's demand pattern, but overlooking the real world demand dynamics. So we are evaluating the real forecasted demand dynamics to evaluate the practical values of accuracy of demand forecasting on the control of operation and the control of the network. So these are the introductions of my PhD and the results and some lessons I learned from during my PhD. I think machine learning is quite a promising technique because it can really enhance our understanding of the data, improve the forecasting accuracy, and enable the good data-driven solution in the engineer application. But machine learning is not a panacea. So we should consider when we met the engineering problem, we should first consider about whether it is suitable for a machine learning application or not. Probably probably is already enough to only use like traditional or simple models. You can already got good results, and also it's simple. It's more simpler to communicate with decision makers. And also enhancing the interpretability and the trustworthiness of machine learning models is critical for effective communication with people, especially they do not have technical expertise to help them better understand how the model makes the decision. So that's it. Thank you for listening.
Thank you so much, Wenjin. It is incredible to see so many years of your work summarized in a presentation. It's really incredible. And having worked with you, I feel very, I feel like it's a very special moment for me as well. I hope the audience also felt the appreciation for this. So thank you. I will now pass on to Wenjin's PhD supervisors, Andrea Cominola and Andrea Castelletti, for a discussion part. So over to the two of you.
Thank you very much, Pauline, and of course, thank you, Wenjin, for the presentation. I can go first with few remarks and then hand over to Andrea for, say, a more compelling discussion and outlining of the challenge and open question in Wenjin work. What I want to point out, and I guess most of you will agree with my remarks, is the uniqueness of Wenjin work. Actually, the thesis addresses a very challenging topic, which is the one of understanding, characterizing, and predicting urban water demand across different spatial and temporal scale. And this diversity of scale is a key and challenging element of Wenjin work, because what we discovered, and actually Wenjin has very clearly presented, is that building a unique model of water demand, we predefine drivers and we predefined underlying cause-effect relationship or mathematical relationship between drivers and the target variable is basically impossible. So what we need are approach, more than models, we need meta models, so approach to build models which can be customized depending on where you are in terms of spatial domain and temporal resolution, because we saw through benchmarking results that drivers of water consumption may be different if you are in Southern California with respect to Northern California, if you are in the United States with respect to Europe. But if you are in Europe, they may be different if you are in a industrialized, rich area or in a underdeveloped urban or peri-urban or rural area. So having this methodology is particularly important. So this is where I see Wenjin contribution is really, really solid and a novel one. Second point is the use of artificial intelligence, because this type of flexibility, so the ability of adapting feature selection, so tools to select across a broad range of candidate variables, candidate drivers, the most significant one, and then build the more performing, the more accurate mathematical mapping between drivers and water demand is a challenge. And so artificial intelligence provide the flexibility of adapting to different contexts and say digesting the variability which is inherent to the problem. Of course, as well, again, described by Wenjin work, the use of artificial intelligence comes with a number of challenge and also potential limitation. The main one, particularly in a context where we want to use model to inform evidence-based policy, so to inform decision-making, explainability is a key element. So this is one of the quite important contribution by Wenjin work, the idea of starting exploring causality detection algorithms. So algorithms which are able to explore and consolidate physically meaningful relationship between drivers and target. We all know that correlation does not apply causation. This is particularly true for a machine learning approach. But with Wenjin work, we've been exploring new avenues to try to make more solid this type of analysis and say retrieve from multiple all accurate description of the mapping between drivers and water demand consumption, those which seems to be more, say, realistic by the point of view of the physical and socioeconomic process underlying this relationship. And my final remark is more, say, well, I have two half remarks. One is about the completeness of Wenjin work, because she's been studying the characterization of drivers, building predictive models, but the last part of the Wenjin work was translating prediction into actions. So it was about designing strategies for controlling water distribution systems informed by this water demand prediction. So she has been exploring all these steps of the pipeline from data understanding, data analysis, characterization, causality analysis, predictive model building, and control. And in this unique journey, I think it was very important, and that again is a unique opportunity provided by NEWAVE, the interaction with industrial partner and other academic institutions. So Wenjin has been spending part of her PhD in Berlin, working with Andrea at U Berlin, but she also been working with KWR, which is a company, a private company funded by water utility in the Netherlands and partly in Belgium, but is an industrial partner basically. So she has also been exposed to real world requirements in shaping and designing tools to reply to challenge which originally were research challenge. So with that, I guess I provided an overview of what are, in my opinion, and also Andrea Cominano's opinion, of course, we've been discussing together this remarks, the main contribution and novelty and also policy implication of Wenjin work. So with that, I'm handing over to you, Andrea, for part of the discussion.
Yes, thanks, Andrea. This really paves the way for a few highlights, which I'd like to add and basically hopefully set up a discussion. I see that there's already a question posted there, but hopefully more questions can come up as well. And I have here some directions which actually could be possibilities for question. I guess Andrea Castelletti has really nicely summarized the interdisciplinary nature of Wenjin's research, the also academic value, but also and scientific value in relation also to the practical value and some challenges related to the method. So I'd like to exactly build on these 3 points, because as part of any PhD, I would say, any PhD work, basically the output is twofold. On the one side, we have some progress on a specific or broad topic, and that's basically where then the PhD student really becomes an expert. In this case, Wenjin became an expert in that field. But on the other hand, we also have a lot of open questions. So of course, you start with one question for the PhD, you complete the journey, and then of course you have results, but also more questions. So I would like really to build on the PhD journey and basically maybe highlight and at the same time set up some points maybe for a reaction on your side later, Wenjin, exactly about this. So the first one is that while now we see the shiny phase of your PhD research, of course, there's been some challenges on the way. What I can think of is data gathering at the beginning. for instance. A second thing that I can think of is in the last part, really, once we had a really nice package of solutions for water demand forecasting, how to integrate them in the control of water distribution networks. That's not really trivial at all. So I'd like maybe from really your perspective as a PhD student, if you can comment on what was the main challenge in this. And after that, I think there's a couple of other aspects which could open really broad discussion. I don't want to take too much time on that, because then it's nice to hear also from the audience and back from you, Wenjin. But basically, one really related to the scientific aspect. Andrea Castelletti has already highlighted the value and the challenges of artificial intelligence methods. And he mentioned really these three key terms: correlation, causation, and explainability. And now, of course, you have tried the first step in this causation. I'd like to understand really how far we are in that in general, and how this relates to explainability, because in a way, I think that causation would be nice to better communicate concepts to those that need to take decision, because they can say, okay, here there's a mechanistic effect. It's not just a correlation, so I can take a decision. But then if we need a neural operator to come up with something that is causality, that might make it a bit harder for operators and decision makers to really understand. So how really far are we in moving from correlation to better causation or causal inference and explainability? And the third aspect is more on this practical side. So the PhD research, the academic value, and then the relation with practice. In a way, I think one output of your research is that you really managed to do an improvement to provide an advance in water forecasting, water demand forecasting models. Now, what is the practical value of this? So is this a few percentages of an improvement in the model accuracy a value for decision makers? And basically, to which point this is an improvement? Is the model accuracy the real improvement? Is the better usability? Or rather the fact that now with more data coming up, maybe using very much traditional modeling techniques might be quite limited, and therefore with the machine learning and the AI methods, we can really make the best out of this data, as we used to say all the time. So I think these could be points for discussion, and possibly also for future PhD research. So I don't think we need to give an answer to these many questions today, but maybe some opinions on your side, Wenjin, and then of course the open discussion with the public.
Yeah, thanks, Andrea. Thanks for your comments and discussion points. I think the first one regarding the PhD challenge, I agree a lot with you about data and the final control work. So the first about the data, I think NEWAVE people also know a lot about me saying I don't have enough data to analyze, and because at the beginning we want to collect more data from different European cities, but there's always an issue that people care about the data privacy, and if they don't know you, they are not really willing to share the data with you. And also, like I remember the last time we almost signed a contract with a Spain company, but they realized I only have 1 year funding, and said no, it's not enough for us to share data and follow up a project with you, so we cannot share the data with you. So it's hard to convince more people to share data with you, especially in Europe, because we have strict regulations to protect the data. But still, that's why I think the initiatives for the public platforms are quite important. For example, the second research, I used the data from public data of the whole US shared on the public platform. So I know there are also some ongoing initiatives in Europe to encourage sharing of the data. So I hope this will like address some challenges of the other PhD students who also rely a lot on more data to analysis, especially when you use data-driven modeling. So if you don't have private enough data, try to find more public resources is one solution to continue with your research, I would say. And then about the control part, I would say it's not only the control issues, let's say. It's more like when your scientific research output comes to the reality, it's really can directly used on the engineering practice, because for the last part of research we are doing now, we are considering the real water distribution network, which is quite complex actually, because in research, in other control research, they probably use only the simplified several nodes, several pipes, a very simple network to test the control strategies or the other strategies you want to test. But in our case, we actually consider more complex one. So when you get the when you are thinking it should work in the reality, but in reality, it might not be working because the reality is much more complex than you thought. So I met quite a lot small problems. I don't know why, because I'm not really understanding that real system. So sometimes I cannot really find the where is the problem, which node has which real setup. So it's really hard to let's say bring your pure scientific research to the to a very real case study. So my reflection would be when you're considering the bring your work to industry, you should better understanding the real case study. So talk more with the water utility people who are managing this network to get really know what happens in this network, and then try to do some modifications or adaptations to better adjust your algorithm with to like fit to this real case study. So I think this is one important lesson I learned from my PhD. I think this also answered the third discussion point about the real values of the demand forecasting. So it's still kind of have a gap between the demand forecasting to the reality, but we are trying our best to merge these two parts. Even we have challenges, but we are addressing at least most of them now. Still it's challenging, but I think it will work pretty soon, because we now understanding much more better than before of the network. So yeah, I mean, it's promising but challenging, but just keep going. I think it's very important. And then the second discussion of the causality, yes, it's the first step of my research to consider about the causality behind the complex system. So I think from traditional model to traditional neural network model, both of them are actually mapping the correlations, either the simple linear correlation or the nonlinear correlation, or yeah, they are all kind of like correlation, but now we are paying attention to the interpretability and explainability of the model to better inform the decision maker. So we tried this a simple causality to indicate we select this predictor because this predictor improved the prediction of the model, but it's probably not a real causality. So in other field, they are using some more let's see, complete choral inference methods, which we probably can borrow to our research field to check the real causality between the drivers and the target variables. So I would say it's just a start, and I think this choral inference included in the forecasting model could have a good promising ways to to negotiate and to communicate your result better.
Thanks a lot.
Thank you so much. Thank you to both discussants. Thank you so much, Wenjin. We're slowly running out of time, so I wanted to pose a question to you that was posted by one of the members of the audience. And it's essentially asking you to perhaps take a step back and look more at the governance aspect. So specifically, the question is about the perception of the water managers and users regarding the models that you were testing. And perhaps if I could add to that, I wanted to ask also about the uptake of the different suggestions and the different technologies by, for example, policymakers. Do we see that? Is there perhaps certain kind of pushback? How does it look on the more political realm?
Oh, it's a difficult question, I would say, because my research is more focused on the technical aspect. But from my perspective, I think this technological improvement is quite important, and also it depends on what's the purpose of your decision making context. So, for example, for the water utility, it might be useful for the water utility to have an accurate model for hourly, daily, weekly forecasting to better manage the operations of the network. But for the like policymakers of a city, of a region, of a country, for them, they probably more concerned about how to manage the water supply and the demand, balance the supply and the demand in the like seasonal scale or yearly scale to better like balance the supply and the demand, right? So in that case, you probably adopt different forecasting models, probably not machine learning, probably the scenario approach. So I would say it's really the governance aspect comes in with its purpose. So like which stakeholders with which goal, and how can these data-driven solutions can help them to understand better the future water consumption or the previous water consumption, and how they make targeted demand strategies of different groups.
Perfect. Thank you so much. And perhaps one last question is also for you to reflect back on your doctoral journey, and what is it that really stood out for you? Maybe something that was particularly challenging. And I think, as Andrea mentioned, working truly across many different actors and engaging with industry, I could imagine that was something quite memorable. But what is it that you look back to and remember fondly, so to say?
Looking back to my PhD journey, I'm quite happy actually with working with Andrea Cominola in TÜV Berlin and the people from industry. I think it's quite unique actually, because working in the industry and working with people from university are quite different. In industry, you have a lot of chance to get to know the real question. And probably you don't need such a fancy model, complex model, but you really need a model to solve the problem. But for research people, probably we are focusing on we should improve the model performance and to have more better results. But we overlook the real practice. So that's why we came out for the last research question of applying the demand forecasting model to a real case study. I mean, it's challenging, but I'm happy to develop such project because I really link the scientific part with the industrial part. So yeah, I think it's quite a nice practice for a PhD.
Thank you so much. I'm going to open up once again to your PhD supervisors if there's one last question.
No questions on my side, but maybe just a consideration based on this previous question that you asked also, that was asked actually by somebody in the audience about this uptake also from the policy aspect and what are utilities. I think there's a lot of lessons learned there from Wenjin, but also from other research connected to it that our groups are doing. And definitely one thing that we've learned, there's a survey we've been running with several utilities, is that in general, many utilities have in fact started this, we can call it Water 4.0, digitalization, digital transformation, whatever you want to call it. That thing is something that many of them really have started, but the picture is still quite fragmented at the moment. And interestingly, what was found out of this survey is that basically you need to really have two main elements, if not three, to push them basically to really adopt digital technologies, which include also AI. And the first one and second one are quite interesting because it's definitely the regulatory framework. There should be some enablers and not some obstacles from the point of view of regulations. And the second is definitely also the economic factor. Even though many utilities are public, revenues are probably not their main target and so on, still they need to survive and be financially sustainable. And so for many technologies that are still brand new and maybe not standardized or not widely adopted, then they might be hesitant in taking them up quickly. So I think these are a couple of lessons that we have on that aspect.
Thank you so much. Thank you. I think it was a great addition. And I have to say, you're doing pioneering work then, Wenjin. I think it's a very nice note to end at. So I would like to thank the audience. And I would like to thank, of course, Wenjin for your time and the contribution. Thank you, Andrea Cominola. Thank you, Andrea Castelletti, for your additions as well. And I would like to spend the last moment to just announce the upcoming remaining sessions, which hopefully will load because I wanted to show you the schedule, but I am realizing that perhaps it is not meant to be for us in this moment. Let me see. Let me try again. We have two remaining sessions. One happening on the 4th of December by Alejandra Burchard-Levine on water consultancies, and one on the 11th of December on water crisis by Paulina Raniecka, who happened to be me, actually. So I hope to see you there. And for those who missed the previous sessions, they are all uploaded on our YouTube channel, on the NEWAVE Network YouTube channel. So please go and revisit or watch for the first time some of the other seminars from our other early stage researchers. And a big thank you to our partners. And thank you for your attendance once again. Wishing you a great day. And until next time.
Thank you for your moderation, Paulina.
Bye-bye.